Hi everyone, this is lecture 1 of mathematical methods for engineers. That's a required course at the University of Notre Dame. Most of the students, the PhD students in engineering, have to take this as their starting course in mathematics. So the first lecture is going to start with extremely basic things related to notation we use for vectors and matrices. And about a third of the course is going to cover fundamental topics in linear algebra. Some of the topics will be new to you, some may be familiar, but in the approach certainly is going to be looking a little bit different. So let's start the course and discuss a little bit about basic things on vectors and matrices. The reference that we're going to use for practically most of the lectures in linear algebra will be following the textbook by Professor Strang. Not only this is the best textbook for linear algebra, but there is an enormous amount of resources in Professor Strang's website. The resources include videos from his courses, homeworks over many years, programs for linear algebra using MATLAB, and many other resources. So this is the textbook we're going to try to follow, starting basically from the lecture today. Okay, so let me start with a few elementary things with vectors and matrices, nothing new to any of you. So what is a matrix? A matrix is an array of numbers, the way that you see here, but also can be an array of anything else. These are all functions, so every element of the matrix is a function of x. You can even have a matrix of a matrix or anything else you can imagine, but certainly anything that we have an array of something, we call this a matrix. So you notice the matrices here are not rectangular. This is a matrix 2 by 3. This is a matrix 3 by 3, 2 by 2, and here these are special matrices that we call them vectors basically. This is a row vector, which is 1 by 3, and this is a column vector, which is a vector 2 by 1, if you think of it as a matrix. So obviously we just discussed about the elements of the matrix, and again remember the elements don't have to be numbers, can be anything else. We discussed about the rows of a matrix. So this is row 1, this is row 2, and similarly for this first matrix we have 3 different columns. These are the vertical lines of entries of the matrix. We're going to make extensive use of manipulations of matrices using rows and columns, so try to become accustomed to how to do this type of calculations. All right, so here is the most familiar matrix to all. This is a rectangular matrix 3 by 3. And the indices, again, if we pick up, let's say, an index like A32, the 32 here means row 3, column 2, and we will follow the same notation regardless if the matrix is square or not. Okay, so vectors are very special type of matrices. So if you think of vectors as an entity that comes from matrices, this is a matrix basically that has only one row, and we call this the row vector. And here is a column vector, so you can think of this as a matrix that basically has only one column. Now later in the lecture today, you will see that there is a way to start with vectors and produce matrices, but the way we have seen it up to now, we define these row and column vectors by starting with matrices, and then in the special case of having only a row or only one column, we get vectors. So the elements obviously for vectors require only one index. And so for example, A3 is the third element of this row vector. A2 on this column vector is equal to 1/2. So we only use one index to describe vectors. Now, a column vector is more or less the standard for the remaining of the course. So when I discuss about vectors, I really referring to column vectors. And so I repeat the notation here. We put these vectors in brackets with the elements inside. And the notation for the column vectors will be letters that they are small case and bold. Now, the row vectors are special vectors as well. And so here is a row vector indicated also in brackets like a column vector, but the elements are shown horizontally, if you like, in a row. So here is one nice example. And everybody's familiar with the concept of transpose of a matrix. So let me just say at this point that you can think of a row vector as nothing else but the transpose of a column vector. So if you have this 5-element column vector and you take the transpose, you get a row vector. So many times when we will be talking about operations with row vectors, we are going to try to think about those operations as operations corresponding to column vectors using this transpose operation. Okay, something that is also used in Professor Strang's textbook. A lot of times you may realize if you use column vectors that have many elements, they take a lot of space. So if we have, let's say, this column vector with 3 elements, another way to represent it is to represent it in inside parentheses with all the elements written in a row. Notice I don't use brackets here, there are parentheses. So when you see something like that, this is not a row vector. To write a row vector, you will have to put these elements inside brackets. If they're inside parentheses, it's basically a simple way to represent a column vector, so you can save some space. All right, so here is a matrix of dimensions m by n. So it has m rows, n columns. The notation of matrices usually is capital letters, bold. All right. If sometimes we violate the rules, hopefully from the context of the discussion, you'll be able to understand if something is a matrix or a vector. At the end of the day, as we said, vectors are matrices, so we are covered that way as well. Okay, so if you have vectors, what do you do with vectors? And the first thing you do is you can actually take linear combinations of vectors. So let me start with some simple example of vectors with 2 elements. So let's say we have vectors v and w with elements v1 and v2 and w1 and w2. So we can define the vector addition as a new column vector that has elements that they are the sum of the corresponding elements of v and w, the way you see here. So you can define also a multiplication of a vector with a scalar. So if you have 2 times the vector v, effectively that vector contains 2 times each component of the vector v. And in this particular case, you can think of 2v as being nothing else but v plus v. If you multiply vector v with -1, you can immediately see the new vector has components minus v1 and minus v2. And of course, you can generalize this and you can take combinations of vectors v and w with any scalar c and d. And I think of these scalars right now as real numbers. Of course, later on we will make these complex numbers, but right now they're real numbers. And so the linear combination of C times V plus D times W is, as you see here, a vector that has components, the corresponding components of V and W, but multiply with the scalar C and D. So C plus 2D and C plus 3D. This ability basically to take combinations of vectors is fundamental to this course in many, many different ways. So please get familiar with this so we don't have any questions as we move forward. Okay, so vectors, as you know from your elementary calculus or high school algebra, you can also represent them with arrows starting from the 0, 0 point in a Cartesian coordinate system and pointing to the right coordinates that correspond to the components of the vector. So for example, here you can see the vector 4, 2 that has 4 in the horizontal direction and 2 in the vertical direction. You see another vector W that has components -1 and 2. And then you can recall from other courses, if you want to add the vector V and W, effectively you get this blue vector that has components 3 and 4. So what we said before, you can also have a geometric interpretation. And here you can think as closing the triangular basically to be able to do this addition. So this is the vector V, and this is a vector that is parallel to vector W. So when you reach that point, you have defined basically the vector V plus W. All right, so here is a little bit different scenario. Rather than adding two vectors, we subtract two vectors. So effectively, we need to subtract the vector V from the vector W. We know by definition of how to do this. We subtract the corresponding components. So 4 minus -1 gives you 5. 2 minus 2 gives you 0. But also we can see this geometrically. So this is V, and we want to add to V the minus W vector. So if this is W with components -1 and 2, minus W has components 1 and -2. You can see here 1 and -2. And then you can simply add the vector V with the vector minus W that is going downwards like this, and you get the vector 5, 0, the way you will expect. All right, so this is the analogy basically with geometry. So effectively, you see here the representation of a column vector 3, 2, with this arrow pointing to the point 3, 2 in the Cartesian XY space. And similarly, this is another three-dimensional vector, or two of them, with components 0, 2, 1. So this point is on the plane YZ with components Y equal to 2 and Z equal to 1. And this vector is on the plane XY with components X equal to 2 and Y equal to 2. And of course, we're not going to remain only in 2 or 3 dimensions in this course. You can extrapolate that the same concepts will actually be applicable to 50 dimensions or anything you want to. Okay, so let's continue talking about linear combinations of vectors. So if somebody gives you a vector U that passes through the origin, okay, no, actually, it doesn't have to pass through the origin. So let's say U is anything you want to, and we want to see what do we get by taking linear combinations of C times U, where C is any scalar. So C obviously can be 0. So C times U obviously passes from the 0 point, but C can be 5, can be 3.5, can be -6, -7. So as you can see on the schematic here, what you actually get if you change C, you get all possible vectors that pass through the origin, and they have the direction of U with plus minus sign. So effectively what you get is you get a line that passes from point 0, 0, 0 that is aligned with the vector U. This is very important. So you can think in 3 dimensions. If you have a vector, you can generate a line in that space by multiplying U with any arbitrary constant C. All right, so let's take 2 vectors now. So let's say we have vectors V and U. So this is the plane where these 2 vectors, the 2 vectors define. And just for no particular reason, the 2 vectors here look that they are normal to each other. And hopefully you're familiar what normal means, but it's not important really in what I'm discussing here. But so we have 2 vectors that define this nice plane. And we want to take an arbitrary combination of these vectors using these constants C and D. But this scalar C and D can be, again, anything you want to. Okay? So they can be 0, which means this combination CU plus D times V passes through the 0.00 point. So what actually we're getting, if we take these combinations of CU plus dV, we get a whole plane, is the plane defined by these vectors U and V that passes through the origin. Okay? So somehow, by using 2 vectors and taking combinations of them, we can fill the whole plane that passes through these 2 points, through the origin 0, 0, 0, defined by these vectors U and V. So the idea here is, if you want to describe any vector on that plane, that vector has to be a linear combination of the vectors U and V. Okay, and it's important here that I emphasize in both discussing about the line and the plane that all of them pass through the point, the origin of the coordinate system that we're using. This will become clear why I emphasize this in a follow-up lecture. All right, and of course, if you had a third vector, assuming some vector that is out of this plane of U and V, so this is very important, right? So if you have another vector that is not on the plane of generated by U and V, then this combination of the vectors U, V, and W literally fills the whole 3-dimensional space. And what I mean, it fills the whole 3-dimensional space, you can take any vector in 3 dimensions, any vector, and you can write it as a linear combination of U, V, and W. So U, V, and W are the generators of this 3-dimensional space. Now, I am starting with some given U, V, and W, and I can fill the whole 3-dimensional space, but there is nothing unique about U, V, and W. I can take some other vectors that they are not all on the same plane, and their linear combination can also generate the whole of the 3-dimensional space. So there is no uniqueness there that we have to worry at this time. Okay, so let's move and remind you a little bit about the inner product of vectors. This is also called the dot product. Let's say you have 2 vectors. I'm going to call them here V and W, and you notice again in my notation I'm making their column vectors, but to save space I indicate them as row vectors, but inside parentheses. So I define the inner product to be a scalar quantity, a scalar number, that is V1 times W1 and V2 times W2. This is my definition, and obviously you can generalize and extend this in 3 dimensions or in 10 dimensions. So this is our definition. This is what we call an inner product between 2 vectors. So if I take the inner product following this definition between these vectors 4, 2 and -1 and 2, notice that 4 times minus 1 and 2 times 2, they give you 0. And that's what we call that the two vectors are orthogonal to each other or perpendicular to each other. You remember this concept from earlier courses, but effectively, if the inner product is 0, that's when we call the two vectors to be perpendicular to each other. Now, I also remind you from your earlier courses, if you take the dot product of a vector with itself, what you get is you actually get the magnitude of a square of that vector. So in some sense, we define here the magnitude of the vector to be the square root of the inner product of the vector with itself. So if you want, let's say, to find the magnitude of this vector 1, 2, 3, so what you do is you take the dot product with itself. All right, so we have 1 plus 4 plus 9 is 14. So the magnitude of V is square root of 14. So you can extrapolate that with this definition, many vectors, most of the vectors will have magnitudes that involve square roots. Very few vectors will come up without a square root, and maybe those will be special vectors. But when you see square roots, that will always remind you that somehow we have computed the magnitude of a vector. Okay, so some trivial examples. If you have this vector, column vector again with components 1 and 2, obviously the magnitude of this vector is 1 plus 4 square root, so it's square root of 5. And here is another vector with column vector with components 1, 2, and 3. So when you take 1 plus 4 plus 9, you get 14. So the length is square root of 14. And, you know, you can see a geometric representation of this that I will not discuss it further, but, you know, you can you can connect the dots with things you already know from earlier courses. And on the top, you see the definition again of the length for a vector with n components. Effectively, everything we say, even if it is in 2 dimensions or 3 dimensions, assume by default that you can generalize it to any dimensions. All right. Now, if we have a vector, we can compute the magnitude. So let me define here what I call a unit vector. A unit vector is nothing else but a vector that has a magnitude of 1. So when u dot u is equal to 1, that's what we call a unit vector. I will give you shortly a way to take any vector and make it a unit vector, do what we call normalization. But first, let me give you the representation of unit vectors in terms of a little bit of geometry here. So let me look on the picture in the right, and I'm working now in 2 dimensions to make life easy. So I and j are the unit vectors in the x and y axis. So I am claiming here that every unit vector can be written in the form of a column vector that has components cosine of some angle and sine of some angle. Right? You agree with me that if you take the magnitude of that, cosine squared plus sine squared, it's 1. So the magnitude of u is equal to 1. So literally, you only need one parameter to represent this unit vector. And this parameter, oops, let me go back. That parameter is this angle theta. And you see here a geometric interpretation. So as you go around this circle, you can generate all possible 2-dimensional unit vectors that we call them here u. Okay, so now this is very important. I'm going to come back to this parameterization in the next slide, but again, somehow we have affiliated with unit vectors a representation through this angle theta Okay, so remember unit vectors by sort of by definition that they have magnitude equal to 1, they take this nice parametric form. Now, if somebody gives you any arbitrary vector, let's call it v here, how do you make it a unit vector? Well, what you need to do is you need to divide by the magnitude of the vector, all right? So if somebody gives you the vector 1, 1, the magnitude is obviously square root of 2, so the unit vector u is 1 over square root of 2, 1 over square root of 2, and if you want to write it with this parameterization using the cosines and sines of an angle, you can see immediately here that the angle is 45 degrees, right? So immediately we can make this to take our parameterization in terms of an angle. All right, so let me make things interesting now. Let me take two unit vectors. I'm going to call one little u, and I'm going to call the other capital U. So both of them are unit vectors. So I claim, using the things we have discussed up to now, that if you take the dot product of these two unit vectors u and capital U, this dot product is nothing else but the cosine of the angle between them. And of course, you're going to ask, why is that? You know, of course, maybe you already know this. Maybe even you use this as a definition of the dot product in other courses. But let's see, based on what we have said about the definition of the inner product, from where is this coming from? So here is my vector u. It's defined by some angle beta, all right? So cosine of beta, sine of beta. My capital U is defined by some other angle alpha, cosine of alpha, sine of alpha. Now remember what the inner product is, right? The inner product will be cosine of beta times cosine of alpha, sine of beta times sine of alpha. And you remember from trigonometry, that is nothing else but the cosine. When you take cosine of beta, cosine of alpha plus sine of beta times sine of alpha, that is the cosine of beta minus alpha, which is the angle theta. Okay, so following our basic definition of the inner product in terms of the components of the vectors, we can show that for unit vectors, the inner product, it is the cosine of the angle between the two vectors. Now, because the cosine in absolute values is less than 1 and greater than 0, you can immediately see here, if you take the absolute value of the inner product of these two unit vectors, this is less or equal to 1. All right, that's an extremely important property that is going to come handy in multiple calculations. Okay, so all of this comes from the fact that the cosine is between -1 and 1, and here we write things in terms of absolute values. All right, now if the vectors are not unit vectors, what can you do? Can you write something in terms of their angles? Yes, of course. If they are not unit vectors, I can show immediately that the inner product is the magnitude of V times the magnitude of W times the cosine of the angle between the two vectors. From where is that coming? Well, it comes from this equation up there, because notice V divided by the magnitude of V is a unit vector, and W divided by the magnitude of W is also a unit vector. And the angle between V or W and W, or the unit versions on V and W, it's always the same. So using this equation that we derive for unit vectors, we can generalize it to any vectors of any magnitude, and we can write that V dot W is equal to the magnitude of V times the magnitude of W times cosine of theta. Now, look at this very nice inequality now, similar to what we derived before for unit vectors, but now if I take an absolute value, I can see that the absolute value of the inner product is less or equal than the product of the magnitudes of the two vectors. This is an extremely important inequality. It's called the Schwarz inequality, and it will come extremely handy in many calculations in linear algebra and literally beyond linear algebra. Actually, if you use this Schwarz inequality, you can show the triangular inequality that some of you, have seen it in geometry in earlier courses. So the magnitude of the sum of two vectors v and w is less or equal than the magnitude of v plus the magnitude of w. And of course, if I ask you where is that coming from, what are you going to say? Can you imagine using the Schwarz inequality and somehow being able to show this triangular inequality? I mean, the derivation is really simple because both left and right hand sides are positive numbers. To prove this, I need to prove also that the square of the magnitude of v plus w is less than the square of the magnitude of v and the magnitude of w. If you expand the square of the magnitude of v plus w as the inner product by definition of v plus w with itself, what will you get? You will get the magnitude of v squared and the magnitude of w squared plus 2 times the inner product of the absolute value of v and w, and that inner product is less than that, and then immediately you can see that the triangular inequality is actually it's true. Okay, just so we can complete these notes, since we talked about the inner product, I remind you what I mentioned this before. If the inner product between two vectors is 0, we call this to be v to be perpendicular to w. And you can show that if two vectors are perpendicular to each other, you have the famous Pythagoras theorem that says the magnitude of a square of v and the magnitude square of w is the magnitude of v minus w squared. And I'm showing to you here with a very nice example. This is my vector v. This is my vector w. You can see by definition the inner product is minus 4 plus 4 is equal to 0. So if this thing is correct, the magnitude of w squared, right? So that's 5, and the magnitude of v squared, that's 20. So we have 25. It should be the magnitude of v minus w squared, okay? And that is 25. And you can see geometrically that the angle between the two vectors is equal to 0. Now, I remind you, we said that the inner product between two vectors is the product of their magnitudes times the cosine of the angle in between them. So if you think of a vector v and you start playing with different vectors w that have different orientations, you can immediately see that for angles from 0, let's say, to 90 degrees, the inner product is greater than 0, okay? Because the cosine from 0 to 90 degrees is positive. Then when this thing becomes perpendicular to the vector w becomes perpendicular to v, so this is 90 degrees, the inner product is 0. And then on the other side, the inner product again becomes negative. Just nothing else but using basically this equation we derived in terms of the cosine between the two vectors. Okay, so now what I want to do, I want to move to something again a little bit familiar, but I want to introduce a new perspective of systems of linear equations, and this will be very useful for the next 2 or 3 lectures in the course. So let me discuss 3 different views of linear equations, AX equal B. All right, 3 different views. So let's say that I give you 2 equations with 2 unknowns. So linear equations, the unknowns are x and y. So 2x minus y equal to 0 minus x plus 2y equal to 3. You can write this in a matrix form as this, right? So this is most probably the most familiar form to all of you, right? So this is the matrix picture of linear algebra equations. But now I want to introduce a slightly different view of reinterpreting these matrix equations. Okay. Again, if you this is my original equations. This is the matrix form. There is nothing new. You can see if you the way you multiply a matrix with a column vector. This will be 2x minus y equal to 2, and I can see here I have a typo in the notes that I will correct after the lecture, and then I see minus x plus 2y equal to 3. Okay, so if so this should be here a 0. Okay, so it's a typo, so we will correct that. All right, so let me discuss what I call the raw view, the raw picture of this linear system of equations. So if you look at the two equations that we started with, these two equations are basically represent lines in 2 dimensions, right? So 2x minus y equal to 0 is basically this blue line that you see, right? You can see when x equal to 0, y equal to 0. When x equal to 1, y equal to 2, right? So this looks like the line 2x minus y. And similarly, this red line is the line minus x plus 2y equal to 3. So obviously, if you want to solve this two system of equations, you are looking for the intersection of these two lines. And in this particular case, immediately you can see the intersection is the point x equal to 1 and y equal to 2. So the raw picture effectively, if you go back to the matrix equation and recognizing that x is going to be 1 and y equal to 2, we are looking at the equations that are derived by taking literally the inner product of each row with this column vector. So 2 minus 1 dotted with 1, 2 gives me 2 times 1 minus 1 times 2. That's the way you multiply matrices with vectors. And this is equal to 0, right? So it's corrected here. And this times that gives me another row. And this is, of course, in our case, is equal to 3. So the raw picture for the case of 2 dimensions corresponds to 2 lines, but in this particular case, they intersect. By the way, I can change the system of equations to something else, and maybe these 2 lines never intersect, right? So we will discuss later on when there is an intersection, so when we have a solution to this type of equations. But right now, we assume that indeed these equations intersect, as in this particular case. Now, if these equations were with 3 equations with 3 unknowns, x, y, and z, so if we were in 3 dimensions, instead of having 2 lines the way we have here, we're going to have 3 planes, and then the intersection of these 3 planes, if it exists, will be a point, which will be the solution to the system of equations ax equal b in 3 dimensions. And again, I emphasize, if there is an intersection of these planes, right? We will discuss many examples where that may not be the case. All right, so let's look at another view of the system of equations ax equal to b. So this is way more interesting than the ones we have seen before. So if you remember my metrics that I had before, had a first column 2 minus 1, second column minus 1 and 2. So what I am going to do is, actually, let me go back. I'm going to show you the metrics again. If you look very carefully in the left-hand side here, a times x, y, I can write this product of this matrix with the column vector x and y as a linear combination of the columns of the matrix A. So actually what I can do is I can write this product as x times the first column and y times the second column. And this is what I have done in here. All right, so I wrote the two equations by having on the left-hand side a linear combination. All right, this is the linear combination of the two column vectors extracted from, these are column vectors of the matrix A. So effectively what in computing x and y, we're saying, can you find a linear combination of these two column vectors that gives me 0 and 3? And of course we know, since we already have done this problem, what linear combination will give me 0 and 3 if x equal to 1 and y equal to 2. So this you will get 2 and minus 2, 0. And for the y component, you're going to get 2 times 2, 4 minus 1. You will get a 3. So we do get the right-hand side, which is 0 and 3. And I indicate the calculation with the equation on the bottom. So again, the key smart idea here is we are writing this as a linear combination of the columns of the matrix A. All right, and we're asking, can you find a combination of those two column vectors to give me this vector 0, 3? And there is a geometric interpretation here. If you take this vector 2 minus 1 and 2 times this vector minus 1, 2, so this is 2 times that, it basically gives you the vector that goes from this point here to a point up in the vertical axis at coordinate y equal to 3. Okay, so linear combination of the columns is what we're looking, and this is our new interpretation here of this linear system of equations AX equal B. And I emphasize again that in this particular example, there is a unique solution of this linear system of equations. So, which means if I take a linear combination of this, I can actually generate this vector 0, 3. It may be possible that these two column vectors are such that there's no way I can generate a vector 0, 3. And we will discuss about this extensively on what type of requirements we have on these column vectors to allow me to generate any sort of vector on the right-hand side of our linear system of equations. This is the vector B that you see there. Okay, so let me summarize. We look at this linear system of equations as a combination of the columns. That's maybe new to you. And then, of course, we looked at the row view of this linear system of equations, where in principle, we take the inner product, we write separate equations corresponding to the inner product of each row. That's why we call it the row view of each row with the vector here, x, y, in the particular case, 1 and 2. Now, when I say inner product of a row vector with column vector, we haven't really defined this inner product between row and column vectors, right? But we have, so when I mean inner product really of, let's say, the row vector 2 minus 1 with the column vector 1 and 2, think of the inner product between the column vector that corresponds to the row 2 minus 1 with a column vector 1 and 2, and similarly the inner product of the column vector that corresponds to the row vector minus 1 and 2 with a column vector 1 and 2. Okay, so we are sort of expanding our horizons and calling this an inner product, if you like, between a row vector and a column vector. Okay, I will not be able to continue on this until the next lecture, but let me just pose the following problem. So we took a matrix A and we wrote AX either thinking of a combination of columns or in terms looking at the rows of A. So my new problem is the following. Can I solve AX equal to B for any B? So if I give you matrix A and if I give you vector B, can we solve this for any vector B given a matrix A? Okay, so if I know A and I throw at you some B, can you solve AX equal B? And I'm just concentrating here only on rectangular matrices AX, rectangular matrices A. So the problem that we will discuss on the next lecture is given A, can we solve AX equal B for all B's? Or maybe for what B's is it possible to solve AX equal to B? And I want you just so you can start thinking of what we will cover on the follow-up lecture. What is A times X? We already discussed that this is a linear combination of the columns of A. So the question of can you solve AX equal B? You can answer it by saying, well, can a linear combination of the columns of A produce all possible vectors B? If the answer is yes, then of course, give me any B, I can solve the system of equations AX equal B. If I cannot do this, we say that the matrix A is singular. So the matrix A is singular when basically I cannot solve AX equal to B for any possible B. You can start extrapolating maybe from earlier courses in linear algebra that effectively if the combination of the columns of A cannot produce all possible B's, that has something to do with the fact that these columns of A are what we call linear dependent. So for example, in our two-dimensional example, we had two column vectors. So how about if those two columns were the same vector? Obviously, with one vector, you cannot produce everything in the two-dimensional space. You remember the picture we had with a vector u and then we multiplied with a scalar c? You can only produce a line that passes through the origin. So a line through the origin, all right, doesn't cover the whole of the two-dimensional space. We need to have two vectors that provide us by linear combination any other vector in that plane. Similarly, in 3 dimensions, if I have a matrix 3 by 3, the two columns need to be able to generate the whole of the 3-dimensional space. If they are not, means that they depend in a way that maybe one is a linear combination of the other two column vectors. So really, when I take a combination of the three vectors, I don't produce anything but a plane. And a plane is not everything in 3 dimensions, right? So we need to be sure that the combinations AX fill the whole 3-dimensional space, and that will be our starting point in the lecture tomorrow to address this question. Given A, for what B's can we solve AX equal to B? All right, that's all with this brief lecture 1, and we will continue the course tomorrow on the same topic, trying to give a little bit more precise answers to the questions we addressed the last few minutes. See you tomorrow. Bye.